Hi everyone. Today I'm going to solve two more examples of open channel flows, especially focusing on Mannings equation. So in the first example, we are gonna investigate the maximum flow rate in a circular channel shape. Which kind of is like an optimization problem. And then in the second example, we are going to go through variable roughness. When we have variable roughness in a channel, what should we do and how we can find a flow rate. Okay, so let's get started with the first example. So in this example, we have a circular channel, as you can see, and it is filled with water up to depth y, which is shown here. So this angle that is made between these two sets is theta. We name this theta, and this is a given in the problem. The diameter of this channel is d. The roughness, Mannings n, is n, and the slope of the bottom slope of the channel is S naught. Okay, so this is the given configuration in the problem. And the problem asks two questions. First, at what depth does the maximum flow rate occur? So we have to find the Q max, or maximum flow rate, as a function of y, and at which y this is going to occur. And we show for certain Q's, for certain flow rates, there are two possible depths. So for some certain values of flow rates, we can have two possible depths in this problem. So for the let's start with the first one. So for the first one, you might think that, okay, the maximum flow rate should occur when y is equals to d, right? The depth, the diameter of the channel. But that is not the case here, and we are gonna show how. Okay. So we start with Mannings equation to find the flow rate, because we want the flow rate in this open channel flow. And so this is the Mannings equation, k over n. N is a Mannings n. K depends on whether we are using SI or British system. A, which is area, RH, hydraulic radius, to power 2/3 times S naught, the bottom slope, to power 1/2. So these are all constant and given in the problem. So S naught is given, and which is Mannings n is given, and kappa or k is also given. So these are all the constants of the problem. And the only two variables that vary based on theta and y are the area of the channel and also the hydraulic radius. So these are the only two variables that we have to find, because as a function of y, the depth, or theta. Okay. So in order to find area, we need to do a little bit of geometry. Okay. So the area is gonna be the sum of two sections. One is this triangle here, which I'm showing here, and I will show you how you can get the area of that. And the second one is this kind of slice here, like pi slice here, with theta degree. Okay, so let's first calculate the area here for this slice, circular slice. So it's gonna be the area of the whole circle is PD square over 4, right? and I have theta over 2 pi of that, right? So I just multiply it by theta over 2 pi. So if theta is 2 pi, it's gonna be the whole. It's gonna this one is gonna be 1. So this means that we have the area, the whole area of the circle is theta. If theta is 0, like this small channel here, which is kind of impossible, but then it's gonna give me 0. If theta is pi, right? Pi means I have like a semicircle or half circle. Then this is gonna be 1/2 of PD square over 4, which also makes sense. All right. So this is how you can calculate the area of this slice. And then we have to add to that the area of this rectangle here. So I show the rectangle here, and the way we are gonna do that is through this. So I define this alpha angle here, this small angle, and I first calculate the area based on this alpha. Okay, so if this is alpha, this is d over 2, right? This is the radius. Radius is gonna be half of the diameter. So this part is gonna be d half, which is this one, times cosine alpha, and this part is gonna be d half. This is gonna be d half times sine alpha, right? So it's gonna be d half sine alpha, and so this is gonna be 2 times d half sine alpha, right? So this section here. So now I can, based on this, I can calculate the area based on this alpha angle. So the area of this rectangle is gonna be this d half cosine alpha, which is written here, times this one, 2 times d half sine alpha times 1/2, right? So if you have any rectangle, you know, this is just a reminder. If this is A, this is B, area is gonna be 1/2 AB, right? So the same thing here I do. So it's gonna be 1/2 2 times d over half sine alpha times d over t half cosine alpha. Okay, so if you rearrange this, this is gonna cancel with this, and we are gonna get d square over 4 sine alpha cosine alpha. Okay, so there is a relation in this kind of trigonometry for sine alpha cosine alpha. So if you remember it from your algebra, sine alpha cosine alpha equals to 1/2 sine 2 alpha. Okay, so I just write it down here. Sine alpha cosine alpha is 1/2 sine 2 alpha, and I know that 2 alpha, which is here, is 2 pi minus theta, right? So 2 alpha is 2 pi minus theta, and the other trigonometry relation is sine 2 pi minus theta equals to minus sine theta. Okay, so these all tell me that sine 2 alpha, which is gonna be sine 2 pi minus theta, is gonna be minus sine theta, right? So now I have a relation for the area based on theta, which is what I wanted. So the first term here, the area, is gonna be this d square this pi is going to cancel out. So it's going to be d squared theta over 8 minus this one is d squared over 8 sine 2 alpha is going to be minus sine theta, right? So this is coming from here. And so I can factor out d squared over 8, and it's going to be d squared over 8 times theta minus sine theta. Okay, so this was a little bit of geometry to find the area of this kind of circular channel, semicircular channel. And then the next thing we need to find is the weighted perimeter. So weighted perimeter is a little bit simpler. So it's gonna be this perimeter here, which starts from here and then you go down here. Okay, so this is the weighted perimeter. So we know this is also is gonna be, if it's for the whole circle, the perimeter of a circle is 2 pi times d half, right? So 2 pi, the perimeter is gonna be 2 pi times r, right? And r is d half, so it's gonna be 2 pi times d half. And then we only have theta of that, it's like a slice of that, so it's gonna be times theta over 2 pi. Okay, so if theta is 2 pi, it's going to be 2 pi times d half, which is what we wanted. If theta is 0, it's going to be 0. So this is the formula for the weighted perimeter. And these two terms are going to cancel out, 2 pi and 2 pi. So we are only left with d theta over half. So this is the weighted perimeter, okay? So now, based on this area and weighted perimeter, I can calculate the hydraulic radius. So the hydraulic radius is going to be A over P, which is d squared theta minus sine theta over 8 times over pi P, which is d theta over 2, right? So d theta over 2, I just wrote it here. And then these two are going to cancel out, d squared over d, so I'm only left with d here. So it's gonna, I will get d times theta minus sine theta, and 2 and 8 are going to cancel, so I am left with 4 theta. So this is going to be the hydraulic radius of my problem in as a function of theta. So now I want to write the Mannings equation. So I have k over n times s naught to power 1/2 times a. So a is d squared times theta minus sine theta over 8 times rh to power 2/3. So it's going to be d to power 2/3 theta minus sine theta to power 2/3 over 4 to power 2/3 theta power 2/3. Okay. Okay, so now I collect all the constant terms here which are given in the problem. So k over n is constant, s naught is constant, d the diameter is constant. I cannot change it in this problem. And the only thing I can play with is theta or y here, right? So these are all the constant terms. I gather them in here. So k over n, s naught to power half, d8, so this 2 is going to be d8 over 1/3, 8 times 4 to the power 2/3. So these are all constant, and I show them as c, right? And then all the variable terms which depend on theta, and this is how I should optimize it, are written in this this part. So theta minus sine theta to power 5/3, because it's going to be 2/3 plus 1, which is going to be 5/3, over theta to power 2/3. Okay. So now I want to find the maximum flow rate, so for which depth. So first I will find theta, and based on that I can find y, right, or depth. It's pretty easy from some trigonometry relationships. Okay, so we reached to this point. This was the last formula we had. So now I want to write, as I said, everything as a function of theta because I want to optimize this channel to find a maximum Q as a function of theta. So all of these things are constant. So I just write them as C and show it here. Then I have theta to power minus 2/3 times theta minus sine theta to power 5/3, right? So this is just this formula that we had, and I wrote Q or flow rate as a function of theta. Okay. So in order to find a maximum theta or a maximum flow rate maximum flow rate as a function of theta, what we need to do is we need to take the differentiate Q with respect to theta and then set that to 0, right? So this was like one of the optimization things that you can remember from your calculus. If you have any curve like this, then you will find the slope by taking the differentiation, and then once this slope is 0, right, then you will have the maximum amount of that function, right? So this is gonna be like the max. So that is the same strategy, or this is the same approach I'm going to use here. So if this is, for example, like x, and this is your function fx, right? So I'm doing the same thing. I differentiate this equation q with respect to theta and then set that to 0 to find a maximum flow rate. Okay, so I want to see in what value, on which value of theta I'm gonna get the maximum flow rate. Okay, so let's start. So first we write the constant term, which doesn't matter, so I just write it here and then multiply it by the terms here. So here we have two terms. So if you remember again from your calculus, so this is like I can say this is like f and this is like g, two functions. And so when you want to calculate the differentiate q with respect to theta or any function, is gonna be f prime, the differentiation for the first function multiplied by g plus f times differentiation with respect to the second function, right? So this is the formula I'm using here. So the first one, first let's take the derivative of the first term. It's going to be minus 2/3 theta to minus 5/3, right? Then I just multiplied by the second function, which is g, which is theta minus sine theta to power 5/3. Okay, so this is just this. And then the second one is going to be f, which is theta minus 2/3, I wrote it here, times g prime. So the derivative of the second function, so the derivative of the second function is going to be 5/3 theta to minus sine theta to power 2/3 times the derivative of inside the parentheses is going to be 1 minus cosine theta. Okay, so this is just this. So then I set this to 0 to get them to find the maximum theta that satisfies this relationship, so I can get the maximum flow rate here. So if I set this to 0, this is just gonna disappear. This constant is gonna disappear, and I only have an equation for these two. So this is gonna be here, I write it here, and this equation I write it on the right hand side. So this is going to be 5/3 theta minus sine theta to power 2/3 times 1 minus cosine theta to power 2 times theta minus 2/3 equals to 2/3 theta minus 5/3 theta minus times theta minus sine theta to power 5/3. Okay, first of all, um, these two terms cancel out. So theta minus 2/3 and theta minus 5/3 are going to cancel out, and I'm going to left, I will only get theta minus 1. Second, as you see, these green ones, which I show, these parentheses, are also going to cancel out. So I'm only left with theta minus sine theta to power 5 to power 1. Again, 2/3 and 5/3 are going to cancel out, and I'm going to get 5 half. So this equation is going to reduce to something like this. It's going to be 2 half minus 2 half cosine theta on the left hand side, and on the right hand side I only have theta minus sine theta over theta. So this simplifies to 1 minus sine theta over theta, and the whole equation simplifies to this relationship: 1.5 plus sine theta over theta minus 2.5 cosine theta equals to 0. Okay, so we need to find this equation, solve this equation to find the theta in which makes the flow rate maximum. Okay, so there are many ways you can find this theta. One is just trial and error, right? So you can guess. So of course theta cannot be less than pi, right? Because if it is less than pi, it doesn't make sense. We don't have such a problem. So theta should be greater than pi, greater or equal than pi in terms of radian, and smaller or equal to 2 pi, right? So this is the range of theta. So you can do some trial and error. So for example, you can start with 1.5 pi and then see where you can get a theta that it can satisfy this. Another way you can do is just put it in a calculator and ask the calculator to solve this for you numerically. And if you do that, or any of these two approaches, either trial and error or doing it with via calculator, you will find that theta equals to 5.28 radian is the value in which it's gonna make this to 0, right? So this is gonna be our optimum value. So just notice that theta is not 2 pi, it's smaller than 2 pi, okay? So now I want to find y. So because the problem asked me what is the depth in which this maximum flow rate occurs, so it's gonna be d over d half, which is from here to here, and then I have it another thing here. All right, so this one, you can say this one is d half times cosine alpha, and this is d half, right? D over 2, which is like radius, and so this one equals to d half over time multiplied by I factor d half plus cosine. Instead of alpha, I just write 2 pi minus theta over 2, right? So 2 pi minus theta is going to be this 2 alpha, and then I'm divided by 2, so I can get alpha. So alpha is going to be 0.5 radian based on this, right? I just said it here. Alpha going to be 0.5, and so the cosine 0.5 is going to be 0.87. And so 0.87 plus 1 over 2 is going to be 0.938 D. And this is the final answer of this problem. So the depth in which the flow rate is going to be maximum is 0.938 D. So remember, the full channel y equals to D does not give me the Q max, and it's somewhere here which gives me the Q max, the maximum flow rate. And after that, if you still trying to fill the channel, the flow rate is gonna be smaller. Okay. So this is an important finding. And then the second question part wanted us to show for a certain Q there are two possible depths. So we can guess what does this mean and where this happens. As you can see, when y equals to 938, somewhere around here, say 938d, we have the maximum flow rate, okay? And after that, if we still fill the channel, the Q is gonna decrease, right? So we should have something like this, something where the Q is gonna increase and then it's gonna decrease, right? And this is gonna be where D equals to Y equals to 938. So we can guess that after that, if we have we can have some certain Qs where, for example, here and here, where these where we can have two depths for those for those certain flow rates. Okay, so in order to be more accurate, we can plot the graph of flow rate versus y. So in order to do so, what you can do, so you have Q here, so you can find theta. Theta is going to be between pi and 2 pi, and you can plot this as a function of you can convert this formula to y, so you get something like qy instead of q theta that we have here based on some trigonometric relations. And then you can plot this. You can plot Q versus Y, or Y over D to non-dimensionalize everything, and Q over Q max, and then plot it for each Y. So you calculate it for each Y, and then you just plot it. Okay, and then if you do this, either you can do this numerically or by calculating several points, you will get something, a graph like this. Okay. So you see, when y over d is 938, you have the maximum flow rate where q over q max is 1. And then you can see when q is full, for full channel, where y equals to d, the q is going to decrease a little bit. So for any q, any flow rate between q max and q full channel, which is between this area, you have two possibilities for y. You have two values for y. For instance, let's say we have here, this is a q which is between q max and q full, right? So it's greater than q full and it's smaller than q max. And you can see that we have two possible y's. So you can get here, you go down, you have y2 and y1, right? So you have two possible y or depths for these certain flow rates. Okay, so this was this finding maximum flow rates and how you can find this and work on these problems. You need to, in this type of problems, these are usually optimization problems, so just note that you need to take derivative with respect to the parameter that you want to optimize. For instance, here I wanted to optimize theta, so I just took a derivative of q with respect to theta. So the first thing is you write everything with respect to that parameter or variable, like it could be theta, it could be y, or whatever that the problem wants from you, and then you take the derivative with respect to that to find the maximum value or the optimum value or extreme value that the problem wants from you. So this is the main approach that you need to take to solve these kind of problems. Okay, so now let's go to the second example for this Mannings equation. So in this example, we have variable roughness in a channel. So we have a channel which has three different roughnesses, and then we want to find the flow rate here. Okay, so the problem wants us to estimate the flow rate in this channel. S naught, the bottom slope of the channel, is 0.002. And then we have three roughnesses. So here, for example, could be rock. Here could be plants, as you can see. Here could be like a, concrete or whatever. So here we have the geometry given in the problem, and also the ends, Mannings n. So in the first one, first part of the channel, we have n1 equals to 0.02. These three parts, they have n2 equals to 0.015, and then this part is a rougher part, like with plants or vegetation. So the n3 is for these two is 0.03. So the length from here is 3 foot, from here to here is 2 foot, and from here to here is 3 foot, and from here to here is 0.8 foot, and the depth of the channel from here to here is 0.6. So this is the geometry of the channel, and we have three roughnesses, and now we want to see how we can estimate flow rate in this type of problem where we have different roughnesses. So the approach that we are going to take is pretty simple. We are going to divide our channel into three sections. So into three sections with similar roughness. So I'm going to divide it in these three sections. So this is going to be section 1 for me. This is going to be section 2. And this is going to be section 3. And then the total Q, the flow rate, the total flow rate is going to be the flow rate of each of these sections. Q1 plus Q2 plus Q3, right? This one plus this one plus this one. And so in order to find these Qs based on the Mannings formula, I need to know their areas, the area of each section. So let's calculate those. A1 equals to A3, as you can see. The area of that is 3 foot times 0.6 foot. It's going to be 1.8 foot square. The weighted perimeter of 1 and 3 are also equals to 3 foot plus 0.6 foot here is going to be 3.6 foot, which is this weighted perimeter, right? And then the hydraulic radius is gonna be for 1 and 3 also equal is A over P, right? Is gonna be A over P, which is 1.8 over 3.6, which is gonna be 0.5 foot. So let's calculate this area and hydraulic radius for second channel. So for 2, A2 is 2 times 0.8, so 2 times 0.8 plus 0.6, right? Because I had this big area. It's going to be 2.8 foot square. P2 is going to be 2 plus 2 times 0.8, right? So only this part is going to be the weighted perimeter, not these, right? I don't consider those. And then the hydraulic radius of this section is going to be A over P, which is going to be 2.8 over 3.6, which is going to be 0.78 foot. So now I write the Mannings formula to find the flow rate for each section. So the Mannings formula indicates QI for any channel is going to be, because I have a British system food, so I, instead of kappa equals 1, I write kappa equals 1.49 over Ni, which is the roughness of each section, times Ai, the area of each section, times RH to power 2/3 times S naught to power 1/2. So using this Mannings formula, I calculate the total flow rate, which is going to be Q1 plus Q3 plus Q2 plus Q3, which will be 1.49 times 0.0002, which is S naught to power 1/2. I factor these out because this is constant for all the 3 channel sections, times the variable things. So the first one is A1. So A1 is going to be 1.8 times RH to power 2/3, which is 0.5 to power 2/3, over N1. N1 is 0.02. Okay, so this is for channel section 1. So for section 2, this is going to be for section 2. Let's review. A is going to be 2.8 times RH 7.778 to power 2/3 over N2, which is 0.015. So I just write it down here. So this is for the second channel, and this is for the third channel. So third one is going to be A is 1.8 times 0.5 to power 2/3 over N3, which is 0.03. So I just write it down. And if you calculate all these, this is what you are going to get. So this will be our final answer for this question. So 16.8 foot cube per second will be the flow rate in this channel with this given information. So now you have learned how to calculate the flow rate in an open channel flow with variable roughness, right? So if you have variable roughness, this is the way you can calculate and you can estimate the flow rate in this channel.